So last time we talked about carboxylic acids and their derivatives. This time we're going to talk about, now that we have a carboxylic acid, what can a carboxylic acid do? So first of all, the carboxylic acids have the last name of acid, so they can behave as acids. They have a pK of around 5. That's one of the pKa's you had to remember from a long time ago. pK around 5. So they are proton donors. Two of the common bases that are used to deprotonate them are sodium hydroxide, sodium bicarbonate, baking soda, things like that. At physiological pH 7.2, 7.3, they are present as the conjugate base, the carboxylate version. So in addition to being acids, proton donors, they can be converted into the other carboxylic acid derivatives. So I told you previously, we will start with writing the acid derivatives in the top corner of our page for a while we're talking about carboxylic acids and their derivatives. Hopefully you remembered acid chlorides, acid bromides come first, then comes anhydrides. Next is thioesters, but we're not actually going to talk very much about thioesters, although they are important physiologically. Regular esters comes after anhydrides, and then amides, then nitriles. Why did we write them in this order? We wrote them in this order from most reactive derivative to least reactive derivative, with carboxylic acids being over to the side because they have this acidic hydrogen that makes them a little bit complicated. We also like writing them over to the side because it helps remind us that carboxylic acids can be turned into an acid chloride. Carboxylic acids can be turned into anhydrides. Carboxylic acids can be turned into esters. Carboxylic acids can be turned into amides. And carboxylic acids can be turned into nitriles. Sort of. There's a detour along the way for that one. But in theory, carboxylic acids can be turned into each of these derivatives. So we're going to start talking about how a carboxylic acid can be turned into this derivative first. Beginning with that carboxylic acid, if you want to turn it into an acid chloride, you're turning an OH into a Cl. Have we seen reagents that will do that before? You betcha. We saw that an alcohol could be turned into a halogen, into a chloride, with SOCl2. As it turns out, there are other reagents that we've also seen before, PCl3, PCl5, SOCl, PCl, PCl3, PCl5. Those are reagents that we've seen before, but we saw them work on alcohols instead of carboxylic acids. They work a lot the same in this regard. We're not going to draw the mechanism for them. These guys, when we saw them with alcohols, were often along with pyridine. Pyridine can be added here as well to be helpful. That's a carboxylic acid being turned into an acid chloride. Next, a carboxylic acid being turned into an anhydride. Well, anhydride means without water. So if I take that anhydride and I remove water from it, 1H, 2H, and an O, I get an anhydride. That one. That's simply a dehydration reaction, and heat will dehydrate that thing to make an anhydride most of the time. Heat will dehydrate lots of carboxylic acids to turn them into anhydrides. P2O5 is not required, but it is a helpful, useful dehydrating agent. We're not going to draw the mechanism of exactly how it works, but it's a helpful dehydrating agent. It assists in the dehydration reaction. If you notice, the anhydride that we made here is a symmetric anhydride, meaning it's got a methyl on both sides of that thing. So it's really just a solution of acetic acid that you heat to make acetic anhydride. Well, this is a symmetric anhydride. But if you wanted to make an unsymmetric anhydride, things get complicated. You can't really use this method to do that dependably. So we will see a lot of reactions that have a lot of reagents, and keeping track of all those little reagents is difficult. But the most common thing that carboxylic acids do when you heat them is dehydrate to form an anhydride. And so the lack of reagents there sometimes freaks out students. Don't let it freak you out. Heating a carboxylic acid typically turns it into an anhydride. So here are two funky little anhydrides. Let's see what we get with these. If we were in a regular traditional class, this is when I would make you predict the products, and I would walk around and view how you're doing. But with it being a virtual class, it's a little bit difficult to do that. So I encourage you to pause the video and give it a shot, trying to predict what products we get in these reactions here. But I can't force you to. So here we go. I'm going to lose water in the dehydration of both of these. And I'm going to end up with that oxygen bonded to that carbonyl. I'm going to lose water with both of these, and I'm going to end up with that oxygen connected to that carbonyl. The mechanism of this is not something we will go over. It's not something you are required to know. You just need to know the most common thing that anhydrides do when you, the most common thing that carboxylic acids do when you heat them is dehydrate. Got it? Good. Moving on to the next carboxylic acid derivative. If you were to take that carboxylic acid and that alkyl halide, along with, recognize it, sodium bicarbonate, what do you get? You guessed it, you get an ester. You get this ester. Well, let's draw a quick mechanism of how. So if I start with benzoic acid, that butyl bromide and sodium bicarbonate. We've said carboxylic acids are acids. So the first thing that happens between these guys is deprotonate that carboxylic acid. Acid-base reactions are super fast. You can't really stop that reaction from happening. When those things are in proximity, they're going to react together like that to make a carboxylate. So then our other thing in solution is an alkyl halide, a primary alkyl halide. So if we go back to our handy-dandy flow chart, what do you expect to happen to a primary alkyl halide? SN2, especially considering that we have an anionic nucleophile. We're going to do SN2. So this O minus SN2 with that guy to get me my ester. We didn't show any stereochemistry here, but we could have made things tougher on you by showing some stereochemistry here with like a deuterium. And SN2 means inversion of configuration. So you got to invert that stereocenter. If we move on to our next example without switching back to the PowerPoint, just moving right along, starting again with benzoic acid, and this time reacting with diazomethane, CH2N2. I really like trying to get students to draw the Lewis structure of this because they realize how rusty they are in drawing Lewis structures from scratch. So you should try to see if you can draw this Lewis structure. But again, just like all the others, we got to move along. And I'll draw it for you anyway. This is one version of the Lewis structure of diazomethane. There's a resonance form of this diazomethane that looks like this. So the nitrogen is negative on the terminal end versus the carbon being negative, and the nitrogen's positive in the middle. Both resonance structures have an octet. This one is your winner chicken dinner, more important resonance contributor, but this one is the one that's going to do something useful for me. This carbon with a minus is going to take the proton from my carboxylic acid. Take the proton from my carboxylic acid, make a carboxylate. That carboxylate, and I've now got CH3 in 2, like this. N2 is nitrogen gas, N2. So it's really like this thing is holding on to nitrogen gas, which is something that really wants to be set free as nitrogen gas. So just like the example from above, our carboxylate did an SN2 over there on that primary alkyl halide. Our carboxylate is going to do an SN2 on that methyl nitrogen compound, that methyl N2 compound. SN2. And we get nitrogen gas as a byproduct, and we get a methyl ester. An ester that has a methyl on this single bonded leg. This little CH3 came originally from my diazomethane. So this is another ester forming reaction. The first one and this one are both make a carboxylate, do SN2. This one up here is creative. You can do a lot of different alkyl halides or other groups that have good leaving groups, like maybe sulfonate esters, tosyls and mesyls and such. But down here, this diazomethane, you're always going to get a methyl ester out of this guy. Always. Methyl ester out of a diazomethane reaction. Moving right along to our next example is the Fischer esterification. The Fischer esterification is going to take me some more space, so let me switch to a new paper. Moving right along to the next example, the Fischer esterification. The Fischer esterification example that I have given you starts with benzoic acid. And this example has methanol as the alcohol that we will react with. And you've got sulfuric acid as a catalyst. It's sulfuric acid, we're going to draw it as H+. If you don't like it that way, sorry, get over it. So this is the first reaction where we are responsible for the mechanism, first of all. And secondly, it's the first reaction that shows us how carboxylic acids and their derivatives react differently than a lot of reactions we've seen previously. This carbonyl carbon, remember, is partially positive, and that's going to be some of the driving force behind why we're doing what we do next. Okay, so this whole reaction starts with an acidic solution. And there's debate among the community about whether this reaction happens first or attacking happens first. I like the mechanism slightly better when you protonate that carbonyl oxygen first. So we're going to say when we have an acidic solution and a carbonyl oxygen, protonate the carbonyl oxygen first. Protonate carbonyl oxygen to get me here. Okay? Attack the carbonyl carbon with whatever nucleophile you've got around. This time it happens to be an alcohol because we're going to make an ester. Note that when I attacked that alcohol, I folded electrons up to that oxygen so that it's no longer doubly bonded. Lose a proton to make a neutral intermediate. What is this base in solution that's doing this? Well, it's likely water in this specific reaction, but the truth is, I trust you enough at this point that we don't have to be obsessed about which exact base it is, but it's probably water. We're just going to use a generic B. So this guy, this is an important intermediate. This is our neutral tetrahedral intermediate. Why does that matter? Why is that a big deal? Well, in the beginning, we talked about this is an sp2 carbon. This carbonyl carbon is electrophilic, and it likes to be attacked by nucleophiles. Well, when you attack this electrophilic carbon with a nucleophile, you're going to end up going through a neutral tetrahedral intermediate, especially when it's in this acidic solution. So sp2 carbon gets attacked by a nucleophile. You end up with a neutral tetrahedral intermediate. This carbon right here has 3 very electronegative groups on it. That's not really favorable. That's not going to sit around for a long time and be our final product. So from this neutral tetrahedral intermediate, you got to keep going. How do you keep going? We're going to make a leaving group and then let it go, let it go. The leaving group we're going to make is water. We're going to do that by taking some of our acid from our acid catalyzed stuff, our sulfuric acid that's sitting around in solution. Protonate one of those oxygens, does not matter which. We don't want to protonate this one because if we protonated this one, we would go backwards to where we started. So protonate one of those carbonyl oxygens, one of those OH oxygens to get me here. From here, we have water. That's a pretty good leaving group. So we could just let it leave and leave behind a carbocation, but I like to go ahead and fold down oxygen's electrons to kick it out. Is it wrong to let it leave, make a carbocation? Absolutely not. The deal is what we're making here and what you would have made otherwise if you made it a carbocation, what we're making here and the carbocation that I'm talking about are resonances of each other. If I'm not requiring you to draw all resonance contributors, you don't have to draw all resonance contributors. So you can draw this guy, or you can jump straight to this guy, because among these 2 resonances, yes, there's one more resonance. Among these 2 resonances, one more resonance of this guy. Really, technically, you could involve the benzene too. Let me be real. Among these 2 resonances, which one is the more important? Winner, winner, chicken dinner? This guy. Because this guy, everybody has an octet. This guy, not so much. So I like to fold down a lone pair from oxygen to kick out my water to get me here as fast as possible. And then we are almost at the end. Some base in solution, probably water, comes to clean up that hydrogen, and ta-da! We have reached the end, and we have made the ester that we were trying to make. Woohoo! Okay, let's clean up our mechanism stuff a little bit. If you notice, from the beginning, I started out with equilibrium arrows, and then I sort of abandoned it. That's because I have bad habits, but really all of this is an equilibrium process, and all of these reactions are reversible. So when I said we want to draw the mechanism to choose to protonate one of these OHs, yes, absolutely. Sometimes this one gets protonated and it takes you reversibly back one step. So the real truth is it's an equilibrium process. It's a reversible reaction. It goes back and forth. Sure. So if we talk about the reversibility of it for a quick minute, how do you favor formation of the products? Sorry. I'm a slow writer sometimes. How do you favor formation of the product in a reaction like this? Well, Le Chatelier's principle says if you remove a product, the reaction will favor formation of more of those products. The easiest product to remove is the water. So carboxylic acid plus alcohol plus extra acid makes an ester. If you remove the water, it favors formation of the ester. Well, I got you here paying attention closely, I hope. Another thing that we will talk about quite a bit is hydrolysis of each of the carboxylic acid derivatives. This is an ester, but hydrolysis of all of the carboxylic acid derivatives will make a carboxylic acid. So hydrolysis of an ester makes a carboxylic acid. Hopefully you can pick apart the word hydrolysis to know that means cutting with water. So if I have an ester and I add tons and tons and tons of water to it, especially in acid catalyzed, it's an equilibrium process. So if I have an ester and I add tons of water to it as an acid catalyzed reaction, I can hydrolyze, I can split that ester back into carboxylic acid and alcohol. So the reverse of this reaction is called hydrolysis. The forward reaction is called the Fischer esterification. Fischer esterification needs to be acid catalyzed. About it, including this mechanism. How does a scientist know that this is the mechanism that's important? This is the mechanism that a Fischer esterification goes through. Among other experiments, one of the experiments that has been conducted here is that you use an alcohol that has an isotopic label on the alcohol oxygen. And then you trace that alcohol oxygen throughout the mechanism and detect where it goes. So if this is the mechanism that's followed, it makes sense that this oxygen, the singly bonded oxygen in the final ester product, is where the isotopic label is. As it turns out, yep, it is. When you run this reaction with an isotopically labeled alcohol, this is the only location where the isotopic label shows up. So that makes sense to scientists to say, this is the mechanism that that reaction undergoes. So there's our Fischer esterification reaction. Here's what we were saying about the mechanism, studying the mechanism to find out how it works. There's our isotopic label on the oxygen, the alcohol oxygen. In the product, it shows up here and only here. Sorry, here and only here. So we've talked about how to turn a carboxylic acid into an acid chloride. We've talked about how to turn a carboxylic acid into an anhydride. We've talked about how to turn a carboxylic acid into an ester, 3 different ways. Now it's time for turning a carboxylic acid into an amide. So I bet you imagine you put this together and ta-da, you get an amide. Not quite. Carboxylic acids are acids. That ammonia or amines in general are bases. So when you put those 2 kids together, you get an acid-base reaction. You do not get an amide immediately. But if you cook and cook and cook this reaction, that was a delta, cook and cook and cook this reaction, you can end up getting an amide out of it. This is not a mechanism we will talk about. It's not a mechanism you're expected to know, because this is really not an easy way to make an amide. It's not the best way. The better way is to activate a carboxylic acid by conversion to an acyl halide or anhydride. What does that even mean? That says it's better to turn your carboxylic acid into a more reactive carboxylic acid derivative. And then once it's an acid chloride, let's say, you can turn an acid chloride into an amide easily with reactions we will discuss soon. And finally, the last reaction of a carboxylic acid derivative is decarboxylation. That's the last one we're going to discuss today. Decarboxylation is rare. It is not a standard, reaction of all carboxylic acids. Let's draw the mechanism for it quickly. If I take that carboxylic acid, that acetoacetic acid that was on your slides, and I just spin it around so that my curved arrows are more easy to draw. I spin it around so that my carboxylic acid part looks like this. This is nice because, and this is common for them to do things like this, because there's a little hydrogen bonding that can happen within that molecule. So we're going to draw this decarboxylation reaction as a cyclic thing happening. This guy, this double bond attacks that hydrogen to make this into an OH. These electrons that were holding on to the H now become a double bond there. That would exceed that carbon's octet, so we got to break one. That becomes a new double bond over there. So decarboxylation, I turned this acetic acid, acetoacetic acid, into CO2, decarboxylation, that means losing CO2. Turned this acetoacetic acid into a CO2, and this. This thing, I hope you recognize, is not typically the way we draw a molecule like this. This thing is an enol. So that thing tautomerizes, oh boy, haven't heard that word in a bit. It tautomerizes to this ketone. So when acetoacetic acid is decarboxylated, it turns into that enol and CO2. That enol tautomerizes to this pink guy, this acetone. The decarboxylation happens when you heat this thing. But wait, I thought you said the most common thing that happens to carboxylic acids when you heat them is anhydride formation. Yep, that's still the truth. The most common thing that happens when you heat a carboxylic acid is making an anhydride. But special acids like acetoacetic acid can potentially decarboxylate when you heat them. What's so special about acetoacetic acid is it's a beta keto acid. So having that ketone in the beta position causes this hydrogen bond, but furthermore, it participates in the reaction to make this enol. A typical carboxylic acid does not decarboxylate, but acetoacetic acid and other similar beta keto acids can. All right, we are almost finished. There's our decarboxylation thing. Some notes about decarboxylations. It's rare. Most acids don't do it. It's common with beta keto acids and things like acetoacetic, which is a beta keto acid. These kinds of reactions are common in biochemistry. Our textbook has some examples, but we're not going to go through them. I've kept enough of your attention for today, so that is all. Thanks.